This is mathematical models and numerical methods involving first-order equations, and in this video we will be talking about compartmental analysis. And let's begin with compartmental systems. These are systems where complicated processes are broken down into distinct stages and modeled by describing the interactions between these stages. So the graphical depiction of a compartmental system is called a block diagram. So a block diagram depicts these systems graphically. Okay, so let's take a look at a basic one-compartment system. So the one-compartment system is suggested with this model. dx dt is equal to the input rate minus the output rate. And so this is the mathematical model for a basic one-compartment system. Now we have x of t is the amount of substance in the compartment at time t. And the input rate and the output rate means how the substance enters the compartment and how the substance leaves the compartment. So here we enters the compartment and the output rate is how the substance leaves the compartment. Okay? So in a mixing problem, we have a one-compartment system. Representing mixing problem. So, as you can see here in this diagram, x of t represents the amount of substance in the tank, or you could say in the compartment. And you can see the rates of the substance entering the tank and the rate that the substance leaves the tank. A lot of times we are given in mixing problems, we are usually given, so we're usually given the rate at which the fluid flows into the tank. So the rate, let's just put input rate. So we're usually given the input rate, and we're also given the concentration in the fluid. Okay, so usually we're given those. So when we are given those, you could say that if we multiply the flow rate, so we have volume divided by and this is our flow rate. And if we multiply that flow rate by the concentration, we will come up with the input rate. Oops, let's write what that is first. So that input rate would be amount divided by time, and that is our input rate. Okay. Now the output rate is a little bit more difficult to determine. So we usually make the assumption I'll put this over there where that orange star is. So we will assume that the concentration is kept uniform in the mixture, and that will help us in determining that output rate. Okay, so going ahead and taking a look at our first example. So here we will consider a large tank holding 1,000 liters of pure water into which a brine solution of salt begins to flow at a constant rate of 6 liters per minute. The solution inside the tank is kept well stirred and is flowing out of the tank at a rate of 6 liters per minute. So that is the same. The input rate and the output rate are the same. They are both 6 liters per minute. So if the concentration of salt in the brine entering the tank is, let's change this color, 0.1 kilograms per liter. And let's go ahead and write what that is. This is the concentration of salt in the brine entering the tank. And of course, this is the input rate, and this is the output rate. Okay, so we want to determine when the concentration of salt in the tank will reach 0.05 kilograms per liter. So we will view the tank as a compartment containing salt. Okay, and so X of T is going to be the mass of the salt in the tank at time T. So right here, this is the mass of salt, that X of T. Okay, so we can find the concentration of salt in the tank by dividing X of T by the volume of fluid in the tank at time T. And we are going to use the model for compartmental analysis. So here we will have dx dt is equal to the input rate minus the output rate. And this is our compartment system. Okay, so now we need to find the input rate. So we are given that the brine flows into the tank at a rate of 6 liters per minute. And since that concentration is 0.1 kilograms per liter, we can conclude that the input rate, so let's look at the input rate right here. We have 6 liters per minute times 0.1, why don't I not use a dot there and I'll use a parenthesis, times 0.1 kilogram per liter. And that's going to give us an input rate of 0.6 kilograms per minute. And that is our input rate. Okay, now we have to determine the output rate. So a few things we need to note. We need to note that the volume is constant in the tank at 1,000 liters. And that is because the input rate is equal to the output rate. And we started with 1,000 liters. So how can we find that output rate? We would just have to have 6 liters per minute, and we will multiply by X of T divided by 1,000, and that will be kilograms per liter. And if we multiply that together, we will come up with 3x over 500 kilograms per minute. So that is our output rate. Okay. Now, the tank initially contains pure water. So that is why we have the initial amount or mass of salt is 0 at time 0. So let's go ahead and use our model here and continue plugging these in. So we have dx dt is equal to 0.6 minus 3x over 500. Now, we also have this IVP because we have x, the amount at time 0 is 0. So that is our initial value problem. This DE is both separable and linear. And we will go ahead and solve this using separation of variables. So if we do that, we will have dx dt is equal to 6/10 minus 3x over 500. And of course, we come up with 300 over 500 minus 3x over 500. And we have dx dt equal to 3 over 500 multiplied by 100 minus x. Okay. So let's go ahead and separate our variables. So we have 1 over 100 minus x dx is equal to 3 over 500 dt. So we've just separated, and now we'll go ahead and integrate. And we have the opposite of the natural log. 100 minus x is equal to 3t over 500 plus a constant. Continuing on in the same fashion, we'll multiply both sides by a negative, and this constant is still a constant. And we will have c e to the negative 3t over 500. And then, of course, we will have 100 minus x is equal to ce to the negative 3t over 500, just taking plus or minus that right-hand side. And finally, we come up with x is equal to 100 minus ce to the negative 3t over 500. Now, using our initial condition, we have 0 equals 100 minus c e to the 0. So c is equal to 100. So finally, we have x of t is equal to 100 minus 100 e to the negative 3t over 500. So let's go ahead and take a look at this solution. So our solution is x of t is equal to, and we'll go ahead and factor that 100 out, 1 minus e to the negative 3t over 500. And we actually can say that this solution will give us the concentration of the salt in the tank at time t. And that will be if we take x of t and divide it by 1,000 liters. So we will go ahead and have, dividing that right-hand side by 1,000, we will have 0.1 times 1 minus e to the negative 3t over 500, and these will be kilograms per liter. Now, to determine when the concentration of the salt is 0.05, we will just go ahead and set that right-hand side equal to 0.05 and solve for T. So let's go ahead and write that out. When is the concentration of salt 0.05 kilograms per liter. So we're going to go ahead and set that equal to 0.05. So we have 0.1 times 1 minus e to the negative 3t over 500 is equal to 0.05. And then we can go ahead and divide both sides by 0.1 and then subtract 1. So let's go ahead and do that. So we have 1 minus e to the negative 3t over 500 is equal to 0.5, and then subtracting 1. From both sides, we have a negative 0.5, and then we end up with e to the negative 3t over 500 is equal to 0.5. So in order to solve for t, we'll go ahead and take the natural log of both sides, and then we will multiply both sides by 500 over 3. We'll go ahead and use a negative. And so we get T is approximately equal to 115.52 minutes. And we'll go ahead and square that off. So the concentration of the salt is going to be 0.05 kilograms per liter after 115.52 minutes. Now I do want to make note of this equation right here. If we have the limit of that function, let's note that the limit of x of t, let's take a look at that limit as t approaches infinity, and that's equal to the limit as t approaches infinity of 100 multiplied by 1 minus e to the negative 3t over 500. And as you can see, as t approaches infinity, this is going to go ahead and equal 100 kilograms. So what is the purpose of looking at that? The limiting concentration of salt in the tank is now able to be computed. So now the limiting concentration of salt in the tank is 100 kilograms divided by 1,000 liters, which is going to be equal to 0.1 kilograms per liter. And this makes sense. And why does that make sense? Because it's the same concentration of the salt in the brine flowing into the tank. Okay, so let's look at this next example. For the mixing problem described in the previous example, assume now that the brine leaves the tank at a rate of 5 liters per minute instead of 6 liters per minute. Now, everything else is going to be the same. We are asked to determine the concentration of salt in the tank as a function of time. So the difference between the flow rate into the tank and the flow rate out of the tank is going to be 1 liter per minute. Using our same one compartment system model, we have dx dt is equal to the input rate minus the output rate. So taking a look at we still have 6 liters per minute multiplied by 0.1 kilograms per liter, and that's going to give us 0.6 kilograms per minute for our input rate. Now, for our output rate, we know that the difference between the rate of flow into the tank and the rate of the flow out of the tank is going to be 1 liters per minute. So let's go ahead and make a note. We have So we have 1 liter per minute. So the volume of fluid in the tank after T minutes is going to be, so the volume after T minutes is going to be 1,000 plus T liters. So that gives our output rate as 5 liters per minute multiplied by x of t divided by 1,000 plus t, and that's going to be kilograms per liter. So since this is 1 liter every minute, that's just going to be equal to t. And that gives us 5x of t divided by 1,000 plus t, and those are kilograms per minute again. So now plugging these into our model, we have dx dt is equal to 0.6 minus 5x divided by 1,000 plus t, and we do still have that initial condition of the concentration of brine is 0 since we have pure water. So now we can go ahead and, so this is linear, so we can write this as dx dt plus 5 over 1,000 plus tx is equal to 0.6. So let's go ahead and solve that linear equation. We have that mu of x, the integrating factor, is going to be equal to e raised to the integral of 5 over 1,000 plus t dt, and that's going to be equal to e, and we can go ahead here and have 5 ln, absolute value of 1,000 plus t. And since t is positive, we can have e to the ln of 1,000 plus t just in parentheses, and we will bring that 5 up. And this is equal to 1,000 plus t to the 5th power. So now we have, let's just come over here to the right, and now we have that the derivative with respect to t of 1,000 plus t to the 5th power times x is going to be equal to 0.6 times 1,000 plus t to the 5th power. So multiplying both sides of that equation by our integrating factor. Okay, so now we have 1,000 plus t to the 5th power is going to be equal to, times x is going to be equal to that integral on the right-hand side, 0.6 divided by 5, so we'll have 0.1 multiplied by 1,000 plus t to the 6th power plus a constant. So now we will have x of t equal to 0.1 multiplied by 1,000 plus t to the, that will just be raised to the 1st power, plus c times 1,000 plus t, and this will be to the negative 5th power, dividing by that, by this term on both sides. Okay, so now using the initial condition, we now have and that would be the negative 5th power. And then if you work that out, you will end up with c equals the opposite of 0.1 times 1,000 to the 6th power. So we can go ahead and now have, therefore, x of t is equal to 0.1. And we're just plugging right back into here and just putting our value of c in there. So we have x of t equal to 0.1 times 1,000 plus t minus, and here is our c, that minus 1,000 to the 6th power multiplied by 1,000 plus t to the negative 5th power. And as you can see, we had factored out that 0.1. So that is the solution to our differential equation. And so now we have the concentration of salt in the tank at time t. We will divide by that 1,000 plus t and come up with 0.1 times 1 minus 1,000 to the 6th power, 1,000 plus t to the negative 6th power, and that's going to be kilograms per liter. Okay, let's now take a look at the population growth model. So here you can see that the change in population with respect to time is directly proportional to the population. And we have K is and that's positive proportionality constant okay, and as you can also see, we will have the initial population at some time equal to P naught. Now we call this the Malthusian or exponential law of population growth. So let's go ahead and write that down. Of population growth. Should be Malthusian law. Okay. Now this is a separable DE. So let's go ahead and find the solution to this initial value problem. So you see here we have the DE, we have the initial condition, so we have an IVP. Go ahead and take that plus off. So let's go ahead and separate our variables. We have 1 over P dP equals K dt. So now we've separated, and we will go ahead and integrate. The natural log of P is equal to KT plus a constant, and we have the absolute value of P is equal to C e to the KT. And now we can use our initial condition at time 0. The population is equal to P naught. So we have, and we can actually finish this up here. This is still a constant, CE to the KT, plus or minus the right-hand side. Okay, so let's go ahead and put P of T. So using the initial condition, we have P naught is equal to C e to the 0 power. So C is equal to P naught. And therefore, we have P of T is equal to P naught e to the KT. And this is the solution of the IVP. So that is where we solve this initial value problem. Okay, so let's go ahead and take a look at an example of population growth. So in 1790, the population of the United States was 3.93 million, and in 1890, it was 62.98 million. Using the Malthusian model, estimate the U.S. population as a function of time. So if we go ahead and set t equal to 0 and in year 1790, how about this? Let's just do this. T equal to 0 represents year 1790. Okay. We also have a data value. So let's go ahead and write down our information. So we have P of 0 is 3.93 million. And we have P of 100, so that would be year 1890. We have 62.98. I'll just put a little star there and there, okay? We can put that below here. T equal to 100 represents year 1890. Okay, so we need to solve for K to come up with that model. So we will use that initial data. So let's go ahead and write our model down that we had before. So we have P of T is our solution equals P naught e to the KT. So, whoops, 3.93. So we'll go ahead and use our data value here. P of 100 equals 62.98. So 62.98 equals 3.93 e to the k multiplied by 100. And if we want to go ahead and solve for k, we have 62.98 divided by 3.93 equals e to the 100k power. And so we have the natural log of 62.98 divided by 3.93. And of course, that's going to be positive, is equal to 100k. So we have k equals 1 over 100 multiplied by the natural log of 62.98 divided by 3.93. And so what we'll have is that k is approximately equal to 0.027742. So now, therefore, we have P of T is equal to 3.93 e to the 0.027742t. And there is the population at any time t. See if we can bring that down a little bit. Now, this model is pretty good up until about 1900. And once you get close to around 1900, this model doesn't take into account for some logical factors. So we do need, note, we do need a logistic model, and that model would take into account for disease, death due to disease, violent crimes, lack of medical supplies. And so this does not consider any of the logical things that might happen. So we do need to assume that there is another component of death other than just death by natural causes. So we could go ahead and mention that this model assumes or considers death by natural causes. So, of course, we do need a logistic model. And we will go ahead and introduce the logistic model. And it looks like this: dp dt is equal to the opposite of A multiplied by P. And we'll talk about what A is in a moment. P minus P1, and we'll go ahead and define these variables. And of course, our initial condition is equal to, at time 0, the population is equal to P naught. So we do have several constants here, and I will define those here. We have A is going to be positive and P naught is going to be positive. We do have the interaction of different population growth constants. And now the solution to the logistic model looks like this. P of T is equal to P1, and we'll talk about these, 1 minus C3 e to the opposite of A, P1T. Now that's the same thing as P naught multiplied by P1 divided by P naught plus P1 minus P naught e to the opposite of A, P1T. Okay, so let's go ahead and use this model in this next example. Taking the 1790 population of 3.93 as the initial population, and given, and here you can see we have two different data values for population, 1840 and 1890, of 17.07 and 62.98 million. Use the logistic model to estimate the population at time t. Okay, so with t equal to 0, let's go ahead and write our data values down. So we have t equals 0 corresponds to year 1790. And then we have two other values. So we have year 1840 and we have year 1890. So this is going to be 100, and of course this is going to be t equal to 50. So we have P of 0 is equal to 3.93. P of 50 is going to be equal to 17.07, and P of 100 is going to be equal to 62.98. So using that data, we can now say here that 17.07 is equal to 3.93 multiplied by P1. So we're using this equation right here, divided by 3.93 plus P1 minus 3.93 multiplied by E to the opposite. Now this is for year 50, A, P1. Okay, now we're going to do the same thing here. We have 62.98 is equal to 3.93 P1 divided by 3.93 plus P1 minus 3.93 multiplied by E to the negative 100 AP1. 1. Now these are both nonlinear equations and we have two unknowns. So we can do a little algebra here and find that P1 is approximately 251.7812 and A is approximately equal to 0.001210. So basically, we have two equations and two unknowns, and we were able to find that. So now we can go ahead and show the logistic model is P of T is equal to 989.5. That's this P1 multiplied by 3.93 divided by 3.93 plus 247.85 e to the negative 0.030463t. Okay, and that's where we multiplied 100 multiplied by A multiplied by P1. Now, we want to make note of a few things. In this equation here, we are able to see that the logistic model predicts a linear relationship between dPdt divided by P and P. Let's go ahead and look at that here. So if we write that down, we have dP dt is equal to the opposite of AP multiplied by P times P1, and now dividing both sides by P, we have this linear relationship between the left-hand side and P. You can see here that AP1 is the, let me go ahead and fill that in. And we have AP1 minus AP. And what you can see here is that AP1 is the intercept. And we can see that the opposite of A is equal to a slope. So we have a linear relationship between 1 over P dP dt and P. Okay, so now if we go back and look at this table of values, you can see this column right here. And here, these are estimated from centered differences. And they actually use this right here in order to determine those. Actually, it was this this left-hand side that they do use. So they go ahead and use centered differences. and then they estimate these values. And then they plot those as shown here. So these values plotted here, these centered differences, are 1 over P of T dP dt, of course, of T, and that's going to be approximately equal to 1 over P of T multiplied by P times T plus 10 minus P times T minus 10, all divided by 20. And that is what is plotted here. And as you can see, we have this scatter diagram. And we have used linear regression. And as you can see here, our regressed line is shown. And so you can see here 1 over P dP dt, and using that linear regression or least squares linear fit, we come up with 0.0280960 minus 0.0008231P. And so this is using least squares regression. And you can see the data here from the table, and then of course the straight line fit. And that concludes this video.